All right, welcome to our fourth edition here of our AP Statistics 2020 review as we go over all the things that we need for the AP exam for this year on May 22nd. So we're now, today is May 8th, so we're now 2 weeks away exactly from the AP Statistics exam, and we finished up Unit 1, so just to kind of recap where we're at, if any of you have missed a day or if you were wondering, on day 1, we went through kind of the introduction to what this course would be. We talked through a sample problem that was given to us about the 2020 AP Statistics exam, and then we also as we went through the very first part, like the diagnostic test, and talked about how we need to do the diagnostic test to kind of see where we're at. Days 2 and 3, the last 2 days we spent on Unit 1. So Unit 1 was exploring one variable data. We talked about, box plots, histograms, bar graphs, different types of those. Main thing we really focused on was questions they're going to ask us on the exam, such as describe a distribution or compare a distribution. And we talked about how that needs to be SOX, or which is the shape, outlier, center, and spread. So those were the big keys from Unit 1, and we're going to move forward now in our kind of our work in AP Statistics here to Unit 2. What I do want to share with you real quick is the Stats Medic course, but I also want to share with you the YouTube channel videos. So if you'll look, there is a playlist. I apologize. I've already given the playlist out with a link, and I'll copy and paste that link again into the chat. But at that link, every day, the videos are being uploaded for each part. So you have online review part 1, 2, and 3 already, and we're in part 4 right now. So if you need to look at those or go back for anything, or if for some reason you do miss a day in one of our 13 days that we have here, then you'll be able to go back and look at that on the playlist. Okay, so I put the link in the chat there for that playlist that will take you to those videos. I also want to make you aware of the AP exam demo video, and that video talks about exactly what's going to be on the AP exam, like how it's going to look, and I'm going to put the links for that also in the chat. I just posted that as well. So that's a look at the AP exam, the demo for that, like how it would look when you go on there. Okay. Any other resources that you may use would be at College Board, so cb.org/AP2020. You want to make sure that you can log in. You want to make sure that you've got your email address confirmed, that you're using the right email address, and you want to make sure that you'll be able to log into AP Classroom when we get to our exam, so that you'll be there for when they send you the exam ticket, and so that you'll be able to get into the exam, okay? So we're going to start with Unit 2, and I'm going to go through real quick and show you my screen. So in video 2.1, section 2.1, or the first part of Unit 2, we call describing a relationship. Very similar to what they call describing the distribution, right? But describing a relationship is basically, what we're basically looking at here is what is the direction, form, and strength on a scatter plot. Those are the three very important things on a scatter plot, are the direction, the form, and the strength. Now, for direction, you're either going to say positive, negative, right, or none. The form would be like, is it linear? Is it curved? What type of form do the points seem to take? And then the strength, you're going to have weak, moderate, or strong. And remember, a very strong linear relationship has an R value close to 1 or close to -1, a very high correlation. You also can tell by the points, all the points are very close to that line of best fit or that least squared regression line. And so that's another thing that makes it very strong. as you go through. And then you see unusual features. So that could be an outlier. That could be an influential point that's far away from the others. That could be a number of different things. But what do you notice that's unusual? And a lot of times that's an outlier about the graph. And then also, anytime you're describing the relationship between two things, you want to use the context of the problem, which in this problem, they're talking about the average temperature outside and your heating bill, okay? So those are the two things. So we're going to talk about that. We're going to talk about at the bottom how to interpret the slope. So interpreting always seems to be a hard part of the problem. It just seems to be something that, like, when we say interpret, it's like it scares people to interpret something. But all we're looking at on here to interpret is we're just looking at what can you interpret the slope, but we want to use it in the context of the problem. And then can you interpret R squared? Now, R squared, a lot of us forget, R is the correlation, which tells us how good of a relationship there is between the data. R squared is called the coefficient of determination. And the coefficient of determination tells us what percent of the data can be explained by the line. So again, we want the R squared to be high because that means that a higher percent of the data can be explained by the line. So all those things are on this sheet for 2.1. So if you have that sheet with you, you can go ahead and pull that out and start taking notes as we go through this video. If you don't have that sheet, then I would like for you to go to the Stats Medic course. If you click on video 2.1, describing a relationship, you can click on the PDF and you can get that and print out that sheet to go with us for Unit 2. So there is the sheet, the Describing a Relationship PDF. So what I would like for you to do is watch along with me this video as they talk about describing a relationship and the beginning of Unit 2. And then once we've done that, if you will, after that, you can ask any questions. We can go over the notes that we've taken or that are on the screen, and then we'll move on to the next section, okay? So I'm going to go ahead and start that now.
Hello, this is Luke from Stats Medic, and you are watching video 2.1, Describing a Relationship. Now, you're going to see a lot of similarities between this video and the previous video that you watched on describing a distribution. The biggest difference here is that when you're asked to describe a distribution, that will be for one variable, whereas this video is all about describing relationships between two variables. So the first thing that you have to know is that this is a common question on the free response for the AP exam, and the rubrics have been very clear over the years on what the expectation is. And once again, there's going to be an acronym for remembering the 4 big ideas to talk about. The acronym here is DUFS, which stands for Direction, Unusual Features, Form, and Strength. And then once again, we're going to want to make sure that we include context in our solution. So let's dig into each one of these 4 big ideas and talk about the options that you have when discussing each of those ideas. So when we look at direction, really you have 2 choices here. The direction's either going to be positive or negative, and that should become very clear to you just by looking at a scatter plot of the data. As far as unusual features, there's really 2 things that you're looking for. You want to look for an outlier, which is a data point that doesn't follow the general trend of the rest of the data, or you may have a scatter plot that has very distinct clusters, and you would want to make reference to that. For the form, generally we're just going to be looking for linear or nonlinear, and most of the examples that we'll deal with will be linear models. And then of course strength, you have a few word choices there. I like using the words weak, moderate, and strong. And there's really not a clear-cut distinction between when it goes from moderate to strong or from weak to moderate. Now, let's take a look at what this would look like in the context of an example. In this example, we've collected data points for 12 different months of the year, and for each month we've recorded the average temperature for the month, as well as the heat bill for that particular month. And you can see we've plotted that on this scatter plot with the average temperature on the x-axis as the explanatory variable and the amount of the heat bill on the y-axis as the response variable. So if we were asked to describe the relationship in this example, here is what would be expected. There is a strong negative linear relationship between average temperature and heating bills with no outliers. So let's make sure that we've actually addressed all four of these and also established context. When I look for the direction, I can see that we have direction here when we've stated it's a negative relationship. Let's look for unusual features. Well, there weren't any, but we did make reference to the fact that there were no outliers. So we've taken care of the U. The form, we can see here that we've identified this as linear, and then the strength, we've identified this as being strong. Now the last thing that we need to look for is to check to make sure that we've established context. And I can see that right here, temperature and heating bills is where we've established context. Now, two other big important ideas that you're going to want to be familiar with is a couple of interpretations. First of all, the interpretation for slope, and secondly, the interpretation of the r-squared value. So let's take a look at those. You can see, placed on top of the scatter plot now, we have a line of best fit, and we've been given the equation of the line of best fit. My first recommendation is that you take that equation that's given to you, and instead of x and y, let's replace that with context. So we've replaced y with the bill, and really here, we want the x variable, which is the average temperature. Now, looking at that equation for the line of best fit, we can see that the slope is the value that is next to the x variable. In this case, negative 3.60. So we definitely want to be able to interpret that slope. And the way that I try and help students with this is to think back to the very first time that you learned about slope. And chances are you learned about it as rise over the run, or possibly change in y over change in x. And in this context, that would be the change in the heating bill over the change in the temperature. And I'm going to write the slope not just as negative 3.60, but negative 3.60 over 1. And so now you're going to see in my interpretation a very close connection between the change in bill of negative 3.60 and a change in temperature of 1. So here it is. For every 1 degree increase in the temperature, we predict a decrease of 3.60 in the heating bill. Now, quick AP exam tip here. When you're interpreting the slope, it is very important that you use this word predict, or you say something like on average. We don't want to say that there's for sure a decrease of $3.60. We want to say we predict a decrease of $3.60. And the other thing that's important too here is we've clearly established the direction of the slope by using the word decrease, which is in reference to the negative value for the slope. Now the other interpretation that you want to be familiar with is the one for r squared. And so if we were given the r value here, and we squared it to get our r squared value, this is just one of these interpretations that is bound to show up somewhere on the AP exam, and you just have to know it. So we turn it into a percent, and we say 98.9% of the variation in heat bills, which is always going to be your y variable, or the response variable, can be accounted for by the least squares regression line. So essentially, you can treat this as a fill-in-the-blank model, where you fill in the blank for what the r squared value is, and you fill in the blank for what the response variable is.
Okay, so as I share with you, let me turn my volume back up. So as I share this with you, we can kind of recap what he went through here. For direction, unusual features, form, and strength. For direction, we're going to say, is there a positive or a negative relationship or a direction? And that's by looking at the line, by looking at the points where they go. Unusual features, are there any outliers or are there clusters? You know, maybe all the data points are down here and then all the data points are here and there's none in the middle. So are there any clusters as well? Form, is it linear or nonlinear? It might be a curved pattern like we talked about. And then strength, is it weak, moderate, or strong? There's no defined numbers for that, but a lot of times we will call a weak correlation between 0 and 0.5. the R value, or between 0 and negative 0.5. We'll call a moderate relationship maybe between 0.5 and 0.8, or between negative 0.5 and negative 0.8. And we'll call a strong relationship a correlation where the R value is from 0.8 all the way up to 1, or from negative 0.8 to negative 1. Okay, so when he described the relationship of this, we said there is a strong, and you can see from the points being very close and the R value being 0.99, there is a strong negative linear relationship. So you see strong gets us the strength, negative gets us the direction, linear gets us the form. So strong negative linear relationship between average temperature use and heating bills. So there's the context of the problem, with no outliers. So even if there aren't any outliers, you need to state that there are no outliers. So that shows that kind of you've checked that. It's almost like when you're checking a condition. Even if you know that it's true, you need to state it so that they know that you've checked it. So you say with no outliers. Now, to interpret the slope, we was talking about, obviously the slope is the number in front of x. So in this problem, the slope is negative 3.6, and the slope is the change in y over the change in x. Well, y is our heat bill, and x is our temperature. So it's the change in heat bill over the change in temperature, and that's negative 3.6 over 1. So that means for every 1 degree increase in temperature, we predict, or we expect on average, right? We predict, or we expect, or on average, a decrease of $3.60 in the heat bill. Now, you cannot say for every 1 degree increase in temperature, the heat bill will decrease by $3.60. And some of you said that during the year. So you need to be very careful on that. That is a definitive statement. Anytime we're making a statement based on the least square regression line, it's kind of like how we do our conclusions and hypothesis tests. We're predicting that this is what's going to happen. We think this is what's going to happen. We have evidence to suggest this is what's going to happen, but we can't say this is what's going to happen, right? So there is a strong negative relationship there. And then for every 1 degree increase in temperature, we predict a decrease of $3.60 in the heat bill. And then lastly, interpreting the R squared. If you wanted to find what R was, all you have to do is take the square root of R squared. And of course, it's a negative because it's going downhill here. But R squared is 0.989. You change that to a percent and you get 98.9%. So the sentence, all I would remember, the only thing that's going to change is the percent, and then when you're talking about the Y. So it's blank percent of the variation in Y can be accounted for by the least squares regression line. So 98.9% of the variation in heat bills can be accounted for by the least squares regression line. And that's all of describing a relationship, which is the first half of Unit 2. What questions can I answer? I'll pause now to answer any questions. If you want to post those in the chat or unmute yourself, I'll take any questions before we begin the second part. Um, 98% of the variation in heat bills can be accounted for by the LSRL. Yes. So I could say 98, I could say, and I'm going to type it in the chat, I could say 98.9% of the variation in heat bills can be accounted for by the LSRL. So yes, I can. I can abbreviate least squared regression line. What does R represent? R represents the correlation. So that is the relationship between the points. R squared is called the coefficient of determination, and that is the percent in variation that can be accounted for by the least squares regression line. So correlation is kind of like their relationship between each other. The closer it is to 1 or -1. When we take the exam, will it give us the slope in R squared, or will we have to find it ourselves? I think they are going to be interested in, your interpretation and your knowledge of it. So I doubt that they're going to really want you to type data in the calculator and find the slope or find the R squared. It's going to be very similar to like a problem like this where they've already given it to you, and their interest is in your writing, right? They're interested in, and in general, in hypothesis tests and confidence intervals, which is the big part of statistics, we're interested in, like, can you analyze the situation? So what they're interested in is, can you take the data that's already kind of done, and can you analyze it? Can you describe it? Can you interpret it? Those are the things that they'll be interested in, I believe, on your exam. Those are good questions. Anybody else have another question? Those are 3 very good questions there. Okay, if not, I'm going to push us to 2.2. So let me look at 2.2 for you real quick. I'm going to pull it up on the screen, kind of overview it. We take this same problem where we talk about the average temperature outside and the heat bill, and now we also add into this problem a residual plot. Remember, a residual plot has your x-axis is the same, it's the average temperature, but now we're looking at their residuals, and a residual is your observed y minus your predicted y. So the observed y is what actually happened, what we get from the table, what the y actually was on that dot. The predicted y is if we plug in the number for x, the temperature for x, that would be the prediction, what the line tells us it should be, or we expect it to be. So residual plots are going to tell us how far away our observed y's were from what was predicted. And again, the closer they are, obviously, the better a graph we get. To have a good linear equation, you want your residual plot to be scattered. You don't want there to be a pattern showing. So it's good for there to be, some people get confused on residual plots. Residual plots, you would like for them to be scattered because some of your predictions you want to be a little bit above and some of them you want to be a little bit below. If all of your predictions are above, then maybe you need to change your line, right? Because your line is too low. If all your residuals, if all your observes are above what was predicted, then you need to change your prediction. If all of your observed y's were below what was predicted, then you need to lower your prediction. But if you have some above and some below and they're kind of scattered, then that means we have a good prediction equation. Okay, so let's go ahead and move to video 2.2, which is predictions and residuals. I'm going to share that with you. And again, if you want to print off the notes, I have the notes for you in the face-to-face class. If not, you can print these off and at the top here, and we'll play through this quick video, and then we'll discuss it and ask questions just like we did in the first one.
Hi, this is Lindsay from the StatsMedic, and you're watching video 2.2 on predictions and residuals. In the last video, we looked at a data set and found a linear regression model where we're comparing the average temperature to the monthly cost or the monthly bill for the heating bill. So in this one, we're going to look at how you could use that regression model to create a prediction. So we're going to find the predicted bill for a month where the average temperature was 42 degrees Fahrenheit. So I have our regression model here. We've got the predicted bill equals 273.58 minus 3.6 times the temperature. So we'll input our temperature, 42 degrees goes in here, and simplify down. It's pretty straightforward. You get $122.38 as our prediction. An AP exam tip, make sure you actually show your work. While this is a very simple calculation, it is still easy to lose points for not showing what you've done. Once we have this prediction, now we're going to turn that into a residual. If the actual bill for the month had been $120, we're going to calculate and interpret the residual. So when you're trying to remember on the AP exam what comes first, the actual or the predicted, you want to remember AP, as in AP statistics. Our residual is the actual minus predicted. So actual always comes first. And if the actual amount was $120, our prediction, as we just found, was $122.38. So our residual is negative 2.38. Now, in your interpretation, you don't actually have to mention the negative necessarily, but you should say that our actual bill for the month was $2.38 less than the predicted bill, which was $122.38. So you don't have to say the negative by name, but you should at least give a direction in your interpretation. It's also very common on the AP exam to be asked if a linear model is appropriate for the data set. A very common student error is students will say, yes, it's linear because the R value is strong. R is not enough to decide if a linear model is appropriate. You want to look for a scatter plot that's showing a linear pattern first, and then you should also look at the residual plot. Your residual plot should have no leftover scatter. So you can see here our scatter plot is looking fairly linear, and additionally our residual plot has no leftover pattern. We're generally looking to see if there's a curve still left in our residuals or clusters in certain areas. Our residual plot shows an even scatter above and below the axis. So this linear model is appropriate. So what if our scatter plot were to show nonlinear data or some sort of curve? So in this scatter plot, you can see towards the end of the graph, we've got some curving in the data. To check to see if a linear model still works, you should make a residual plot. And you can see that the residual plot shows a leftover pattern. There's a U shape. So we know a linear model would not be appropriate. On the AP exam, you wouldn't be expected to calculate a nonlinear model. They would usually give it to you. So we've created this nonlinear model to fit the data. It's the predicted log of the bill equals 4.52 minus 1.57 times the log of the temperature. We're going to use that to predict, again, the bill for this month that had 42 degrees Fahrenheit. So remember to make sure you're showing all of your work. When I put in 42 degrees in for temperature, I can really type this whole portion into my calculator and I get 1.97. A very common student error then is to report 1.97 as their prediction, but this is the predicted log bill. So we need to cancel out the log. In order to do this, we need to do 10 to the on both sides. This will cancel out my log here, leaving me with the predicted bill, which is $93.33.
Okay. Okay, so I'm moving, so let me move forward to, sorry, the video here, so off we go. So in 2.2, excuse me, so in 2.2, it said, first of all, we wanted to find the predicted bill for a month with an average temperature of 42 degrees. There's multiple ways of doing that. We could kind of look at it at 42 and you could show that you're going up here and then over, but the most efficient way is obviously to plug 42 in for X, right? So when we're looking for the predicted bill, we would say 273.58 minus 3.6 times 42. That would be the predicted. And then when we went through and found the actual, when we went back and found the actual value, then we could see that since the predicted value was 122.38 after we did the math, that the actual value was 120. And for residual, really important to remember, a lot of people will get this backwards, but it is observed minus predicted, or you might say actual minus predicted. And a lot of people can remember that easily by, so it's the actual Y minus the predicted Y. A lot of people can get that easily by subtracting these, the actual AP, by knowing it's AP, advanced placement, actual minus predicted. So that helps you to kind of remember that. So the actual Y was 120 degrees, so it was actually, or $120. So it actually cost $120 when it was 42 degrees. That's how much it actually cost us. It was predicted to cost us $122.38. So we get a residual of negative 2.38. Okay. So again, is the linear model appropriate for the data? So again, we talked about the R value is really high. So the R value is like negative 0.995, but you also want to have a scattered residual plot. So you have a scattered residual plot. That also helps show you that the linear model is appropriate. And we talked about if you would have seen a really big curved pattern in the residual plot, then we would have known that the linear model wouldn't be appropriate for this scenario. So if it's not appropriate and you have to use a different type of model, the most common one to use is what's called a log model. And so that is so you would go to logarithmic regression and go through that and find the average temperature, okay? In general, you're going to need to know the key from here that you're really, the only things, the main topics that you're going to see probably on the exam are, can you find a predicted number, right, from an equation? So you would not do that. Can you then find the actual number? So we would be able to know at 42 it was actually 120, really just by looking at it. And then can you find a residual? So observed Y minus predicted Y. And then do you know that the linear model is appropriate? How do you base that off of? Well, you base it off of your correlation, but not just your correlation. You also base it off of your residual plot, and you want a scattered residual plot to do that. So again, I don't think you're going to be making a linear regression line. I don't think you're going to be plotting dots. I don't think you're going to be making a residual plot. I think you're going to be analyzing those and using those to make predictions. So are there any questions from 2.2 that I can go over now? Yeah, I would just add the log, yep, to see if the data is nonlinear. But basically, you're going to know if the data is nonlinear just by, you're going to know if the data is nonlinear because you're going to see that the equation, that it's not a good fit here. As you see, this is a great fit, but you'll see that it's not a good fit. And you'll see that your residual plot shows like this very obvious pattern. So it'll be easy to tell that your data is nonlinear because the scatter plot's going to give it away, the residual plot's going to give it away, your correlation is not going to be good. All those things are going to kind of give away that it's not a good linear pattern. I would say that you're more likely to see one that is a good linear pattern, and they may ask you to find a residual. That would be an easy thing, and you really wouldn't even need a calculator, you know, because it would be something easy that they could test you on is, can you find the residual for, they might just say, can you find the residual for the temperature of 42 degrees? And you've got to know to plug in 42 to get the predicted. You've got to know to find the actual, and you've got to know to do actual minus predicted. To get the residual there. Any other questions? here on 2.2. How do you get the R value? Oh, so the R value, I used that from the previous problem. So this is the same problem, just continued. So when I had R squared back in 2.1, it was 0.989. And to get from R squared to R, you take the square root. So I took the square root of 0.989, and that gave me 0.995. But because this correlation is obviously negative, then I know it's negative 0.995. But I took the R value from 2.1, and since we're dealing with the same problem, that's how I knew that was the same R value here in 2.2. So I didn't have to calculate it. It was given to me in the problem. Anything else? Okay, so the next thing that we would like to go to on our list of parts for today, and really almost the last thing, right? Because we're about 2/3 of the way through. So we've done 2.1 and 2.2. So we want to look at the 2017 free response question number 1, and then we want to look at how that would be scored here in Unit 2. So 2017 free response question number 1 is there. If you want the PDF of it, again, you can download it, and I'm going to put it on my screen as we work through it real quick. So let's read the problem. Researchers studying a pack of gray wolves in North America collected data on the length X in meters from nose to tip of tail, and the weight Y in kilograms of the wolves. A scatter plot of weight versus length revealed a relationship between the two variables described as positive, linear, and strong. For the simulation described above, explain what is meant by each of the following words. So if it is positive, if the relationship is positive, what does that mean in this problem? So we're thinking if the relationship here is positive, what does that mean for us in this specific problem? Yeah. So what I would say is, and again, you don't want to be exact. So wolves with higher lengths tend to weigh more, or on average they weigh more, right? So you don't want to say like that as the weight increases, the length increases, because that's like a definitive statement. So you want to say it tends to increase, or on average it increases. That's a really key thing that can lose you a few points. So you want to say wolves with higher lengths tend to weigh more on average, or wolves are as, if you take what Emma says, as weight increases, length also tends to increase, or as weight increases, meters also increases on average. So because it doesn't happen to every single time, but on average it does happen as you go through. Okay, let's talk about linear. So linear just means that the points or our data follows a straight line, right? Pattern. So our data points follow a straight line pattern. That's what it means for it to be linear. So then we get to strong. What does it mean to be strong? What about the data point? If you saw the line and you saw the data points and it was strong, what would you notice? That the points were what? Yep. The points are closer to the line. So the data points are close to the line. That's the key there with it being strong, that your data points are close to the line. They got to follow that line, yes. Absolutely. The data points closely follow the line. All right, so that's our positive, linear, and strong. Now, the data collected from the wolves were used to create the least squares regression equation, y hat equals negative 16.46 plus 35.02x. B, interpret the meaning of the slope of the least squares regression line in context. So we're going to interpret the meaning of the slope of the least squares regression line in context. And so what that's going to be is for every 1 meter of increase, or for every increase of 1 meter, however you want to write that, for every increase of 1 meter in wolf length, we predict an increase of 35.02 kilograms in weight. And you want to make sure you put the units of measurement here. Very important. So for every 1 meter increase in wolf length, we predict an increase of 35.02 kilograms in weight. So that's how you're using the context of the problem to interpret the slope. Okay, so now let's look at C. One wolf in the pack had one wolf in the pack with a length of 1.4 meters had a residual of negative 9.67 kilograms. That was their residual. What was the weight of the wolf? Okay, well, let's look at what the predicted would be. So negative 16.46, right, negative 16.46 times, plus 35.02. And then in parentheses, we would put 1.4 because that was the length of that wolf. So we're going to predict what its weight would be. So the predicted weight, I keep breaking my pencil here. Predicted weight is going to be that equation. That would give us a predicted weight of 32, would it be 30? It should be 32.57. Yeah, I got 32.57. I did that correctly. And then we look at so we need to find what the actual weight was. So let's look. So let's remember a residual equals actual minus predicted. We know the residual was negative 9.67. We don't know the actual. We know the predicted was 32.57. Okay, so all we have to do is add the 32.57 as I scroll down, sorry. All we have to do is add the 32.57 to the left side. So a little bit of a little simple solving equations. And we get that the actual was, and so we have negative 9.67 plus 32.57. So we get that the actual was 22.9 kilograms. And notice I've shown all my work there. Okay, so again, to go through number one, we did positive, linear, strong. Then we interpreted the slope. Then down here it gave us the residual and it gave us the X value. So we're able to use the X value to find the predicted. Now we have the predicted and the residual. Residual equals actual minus predicted. Well, we know the predicted and we know the residual, so we can now solve for the actual. So that was just a little bit of math there and knowing the correct formula. Okay, so let's look over how they would score this question now that we've gone through it and see what it would look like. Okay.
In this video, we're going to take a look at question number 1 from the 2017 AP Statistics exam. So let's first take a look at the question. Researchers studying a pack of gray wolves in North America collected data on the length X in meters from the nose to tip of tail and the weight Y in kilograms of the wolves. A scatter plot of weight versus length revealed a relationship between the two variables described as positive, linear, and strong. For the situation described above, explain what is meant by each of the following words: positive, linear, and strong. The data collected from the wolves were used to create the least squares equation, y hat equals negative 16.46 plus 35.02x. Part B, interpret the meaning of the slope of the least squares regression line in context. Part C, one wolf in the pack with a length of 1.4 meters had a residual of negative 9.67 kilograms. What was the weight of the wolf? So I'm going to take you first through a model solution, and then after we look at the model solution, we'll take a look at the rubric and what was required in order to get full credit. So for our model solution, in part A, we had to give good descriptions for 3 different big ideas here. So for positive, we've stated here that wolves with higher lengths tend to weigh more. And you'll also notice that I've taken care of the context right there in the first part. As for linear, we just said that the points on the scatter plot tend to follow a straight line. And as far as strength is concerned, they said that it was strong, which means that those data points were close to the line. Now for part B, a very common AP type question asks you to interpret the slope in the context of the problem. And so we have, for every increase of 1 meter in wolf length, we predict an increase of 35.02 kilograms in the weight. Now the last part of this question, part C, they asked us to calculate the actual weight of a particular wolf, and they gave us the residual. And so you have to remember the relationship between actual and predicted, and you got to remember the correct order here. Actual minus predicted is what gives you your residual. Now in this problem, we were given the residual and asked to find the actual. So the other piece of information that we need is the predicted weight of this particular wolf. So I've shown the work here where we took the equation for the line of best fit and we've plugged in the length of the wolf at 1.4, which has allowed us to make a prediction for what that wolf should weigh. So we go back here and we plug that in for the predicted value, which allows us to then solve for the actual weight of the wolf. And we see here that the actual weight of the wolf is 22.9 kilograms. Now that takes us through the model solution, but let's take a look now at the rubric to see what would be required for full credit on this one. Now, the way that this one is graded is there are 3 different parts, and in each of the 3 parts, you're going to give yourself a grade of E for essentially correct, P for partially correct, or I for incorrect. The first part is all of part A, and the way that they've defined it for full credit, in order to get essentially correct, you have to have acceptable definitions for all 3, and then you also have to have context. Well, context is easy. We established that right away here when we said wolves and lengths and weight. So we know we've taken care of the context. Now, as far as acceptable definitions, I'm going to run through a list of acceptable definitions and unacceptable definitions for each of the 3 ideas. When describing the positive part of this question, here are some acceptable responses. As length increases, so does weight. Longer wolves weigh more. The points on the graph go up as you move from left to right. Now here are some that are not acceptable for describing positive. As the length goes up, weight changes. No direction there. Both length and weight get bigger. Once again, no relationship described. And the correlation is greater than 0. Okay, the positive relationship part of that is not explained. Now let's take a look at acceptable and unacceptable responses for linear. First, let's start with acceptable responses. The relationship between length and weight follows a straight line. The pattern of points in the scatter plot is relatively straight. Length and weight have a constant slope. And here are some that are not acceptable for describing linear. The points all line up, because they could line up all along a curve. There is a positive correlation. The scatter plot is a line. It's not the scatter plot that is a line, it's the points within the scatter plot that form a line. Now let's take a look at acceptable and unacceptable responses for strength. Here are the acceptable responses, indicating the data points are close to a line, indicating that residuals are small. Correlation is close to 1. Notice there the number 1 has to be there. There has to be a number. Now here are some that are not acceptable. You can draw a straight line through the points. All points are close together. And there is a high positive correlation. Notice there's no reference to the value of 1. So hopefully now you can decide whether you have acceptable definitions for all three. If you do, with the context, give yourself an essentially correct. If you only had acceptable definitions for 2 of them, with the context, you get a partially correct. Or if you had all 3 acceptable definitions, but you forgot your context. Anything less than this would be I for incorrect. Now let's take a look at part B. There are 3 components that are necessary for full credit here. First, you have to correctly identify the slope of the line as 35.02. Secondly, in your interpretation, you have to say that an increase of a specified amount of weight for each unit increase of length. And for us, we've specified an increase of 35.02 kilograms for every 1 meter increase in the length. And then the third thing is you have to have used the word predicted or the words on average. So for us, we put that right here. Okay, we call that non-deterministic language. So one important idea here is if you missed component 1, you can still get credit for components 2 and 3, even if you're using the incorrect value that you used for part 1. So if you got all 3 of those components, give yourself E for essentially correct. If you got 2 of those 3 components, you get partially correct, and then anything less than that would be an I for incorrect. And finally, part C, let's take a look at. And for this one, there are 2 components that are necessary in order to get full credit. First, you have to have calculated your predicted value as 32.57, which is what we have here. And then secondly, you have to calculate the correct actual value of 22.9 with work. So clearly showing that you're using the residual and the predicted value in order to arrive at the actual value here. Now, it is possible for you to get credit for part 2, even if part 1 is incorrect. If you use an incorrect answer and you show your work here, you can still get credit for the actual, even if your answer is incorrect. Now, in order to get full credit on that part, you have to have both components, 1 and 2. If you only have one of those components, give yourself a P, partial credit. So now that you've looked at all 3 parts, and you have either E, P, or I for each one of those 3 parts, here's how you turn it into a
Okay, so what we looked at here is what would be an E, P, or I for all of these questions. Okay, essentially, partially, and incorrect. So if you look essentially correct, if you noticed, a lot of times they're looking for the work to be shown. You heard them say work to be shown, and then you heard non-deterministic language. And what that means is if you use deterministic language, that means you're saying that this causes this to happen. Non-deterministic language means we predict or we expect or on average or it should. And that's what we want to use when we're talking about regression, because remember, this little y hat makes this a prediction equation in general. Okay, so that takes us through the first half of Unit 2. So if you go back really quick, in Unit 2, you look at, we did video 2.1. We talked about describing a relationship. We talked about predictions and residuals, and we went through the 2017 free response question number 1. On Monday, as we come back, hopefully to work together, we will go through the Unit 2 multiple choice questions together. We'll talk about those, and then we'll do another practice free response and look at its solution. And we'll finish up with Unit 2 on Monday. The rest of next week, on Tuesday and Wednesday, we will go through sampling and experiments, and on Thursday and Friday, we will go through probability. So that's a preview ahead to next week. And I thank you all for being here today. If there's no further questions, we'll end today's meeting and we will move forward on Monday.